The statement in Note 2 of Table 450.3b that the secondary overcurrent device shall be permitted to consist of not more than 6 circuit breakers or 6 sets of fuses grouped in one location applies only to services. 240.21c3 is an exception to the general rule that tap conductors must terminate on a single overcurrent protection device. This exception applies only to industrial installations and allows for the use of multiple overcurrent protection devices on tap conductors under certain conditions. To elaborate further on transformer secondary taps and the relevant code requirements, we need to delve into the details of the National Electrical Code, specifically focusing on Article 450 and Section 240.21. The code provides specific guidelines to ensure the safe and reliable operation of electrical systems, and understanding these rules is crucial for electrical engineers, contractors, and inspectors. Firstly, let's consider the function of a transformer. A transformer is a static electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. It typically steps up or steps down voltage levels to make them suitable for different applications. The secondary side of a transformer is the output side where the voltage has been transformed to the desired level. Taps are connections made at different points along the transformer winding to provide different voltage ratios. These taps allow flexibility in the voltage output to match the requirements of the connected load. Now, let's examine Note 2 of Table 450.3b. This note pertains to the overcurrent protection of transformers rated 600 volts or less. It specifically states that the secondary overcurrent device can consist of no more than 6 circuit breakers or 6 sets of fuses grouped in one location. This rule is designed to prevent overloading the transformer and to protect the connected equipment from damage due to excessive current. It is important to note that this provision applies only to services, meaning it is specific to the main electrical supply to a building or structure. The purpose is to limit the number of branch circuits or feeders that can be connected to the transformer secondary, thereby controlling the overall load in the transformer. The term grouped in one location means that all the overcurrent devices must be physically located together, typically in a panel board or similar enclosure. This arrangement allows for easier inspection and maintenance, and it also ensures that the overcurrent protection is readily accessible. Secondly, we'll discuss 240.21c3. This section addresses tap conductors, which are conductors that are tapped from a feeder or transformer secondary and supply power to a load. The general rule is that tap conductors must terminate on a single overcurrent protection device. This means that each tap conductor must be protected by a circuit breaker or set of fuses that is sized to protect the conductor from overcurrent. However, 240.21c3 provides an exception to this rule for industrial installations. In an industrial setting, it may be necessary to have multiple overcurrent protection devices on tap conductors to supply power to different loads or pieces of equipment. This exception recognizes the unique needs of industrial facilities, where electrical systems are often more complex and require greater flexibility. The exception in 240.21c3 allows for multiple overcurrent protection devices on tap conductors under certain conditions. Firstly, the tap conductors must be protected from physical damage. This can be achieved by enclosing the conductors in conduit or other protective raceways. Secondly, the tap conductors must be no longer than 25 feet. This limitation is intended to minimize the risk of overcurrent in the tap conductors. Thirdly, the ampacity of the tap conductors must be at least 1/3 of the ampacity of the overcurrent device protecting the feeder or transformer secondary. This ensures that the tap conductors are adequately sized to carry the load. Fourthly, the tap conductors must terminate in a single circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. This is the final overcurrent protection for the tap conductors. It is crucial to understand the distinction between the rule in Note 2 of Table 450.3b and the exception in 240.21c3. The former limits the number of secondary overcurrent devices to 6 per service, while the latter allows for multiple overcurrent protection devices on tap conductors in industrial installations only, provided that certain conditions are met. In practical terms, This means that in a typical residential or commercial service, you would be limited to no more than 6 circuit breakers or sets of fuses on the secondary side of the transformer. However, in an industrial facility, you could have more than 6 overcurrent protection devices on tap conductors, as long as you comply with the requirements of 240.21c3. To further clarify these concepts, let's consider a few examples. Imagine a small commercial building with a 75 kV ampere transformer supplying power to the building's electrical system. According to Note 2 of Table 450.3b, the secondary side of the transformer can have no more than 6 circuit breakers or sets of fuses. These overcurrent devices would protect the various branch circuits that supply power to lighting, receptacles, and other loads throughout the building. Now, let's consider an industrial facility with a large transformer supplying power to various pieces of equipment. In this case, the facility may need to install multiple tap conductors to supply power to different machines. According to 240.21c3, the facility can use multiple overcurrent protection devices on these tap conductors as long as they comply with the requirements for conductor protection, length, ampacity, and termination. In addition to these specific rules, it is also important to consider the general requirements for overcurrent protection in the National Electrical Code. Article 240 provides detailed guidance on the selection and installation of overcurrent devices, including circuit breakers and fuses. These devices must be properly sized to protect the conductors and equipment they supply, and they must be installed in readily accessible locations. The code also requires that overcurrent devices be approved for the intended use and that they be properly maintained to ensure reliable operation. Regular inspection and testing of overcurrent devices are essential to verify that they are functioning correctly and that they will provide adequate protection in the event of an overcurrent. In summary, the code requirements for transformer secondary taps and overcurrent protection are designed to ensure the safety and reliability of electrical systems, while limiting the number of overcurrent devices on services and by providing specific rules for tap conductors in industrial installations. The code helps to prevent overloading, short circuits, and other electrical hazards. Understanding these requirements is crucial for anyone involved in the design, installation, or maintenance of electrical systems. In addition to the points already covered, let's consider some additional factors related to transformer protection and tap conductors. One important consideration is the transformer's impedance. Transformer impedance is the opposition to the flow of alternating current, and it plays a critical role in limiting the fault current during a short circuit. Transformers with higher impedance will limit the fault current more effectively, which can help to protect the transformer and the connected equipment from damage. The impedance of a transformer is typically expressed as a percentage of the transformer's kilovolt ampere rating. For example, a transformer with an impedance of 5% will limit the fault current to 20 times the transformer's rated current. The National Electrical Code requires that transformers be protected against overcurrent based on their impedance. Transformers with lower impedance require more sensitive overcurrent protection to prevent damage during a fault. Another important consideration is the coordination of overcurrent devices. Overcurrent coordination is the process of selecting and setting overcurrent devices so that they will operate in a coordinated manner during a fault. The goal of overcurrent coordination is to ensure that only the overcurrent device closest to the fault will operate, while the other overcurrent devices remain closed. This minimizes the extent of the outage and allows the rest of the electrical system to continue operating. Overcurrent coordination is typically achieved by using time current curves, which show the operating characteristics of the overcurrent devices. By carefully selecting the overcurrent devices and adjusting their settings, it is possible to achieve effective coordination and minimize the impact of faults. In addition to overcurrent protection, transformers also require protection against other hazards such as overvoltage and overheating. Overvoltage protection can be provided by surge arresters, which are devices that limit the voltage to a safe level during a surge. Surge arresters are typically installed on the primary side of the transformer to protect it from lightning strikes and other voltage surges. Overheating protection can be provided by temperature sensors which monitor the temperature of the transformer windings. If the temperature exceeds a safe level, the temperature sensors can trip a circuit breaker to energize the transformer. This prevents the transformer from being damaged by overheating. When installing tap conductors, it is important to follow the code requirements for conductor size, ampacity, and protection. The tap conductors must be sized to carry the load they supply, and they must be protected against overcurrent by a circuit breaker or set of fuses. The code also specifies the maximum length of tap conductors, which depends on the ampacity of the conductors and the type of installation. In addition to the code requirements, it is also important to consider the practical aspects of installing tap conductors. The conductors must be properly supported and protected from physical damage, and they must be installed in a neat and workmanlike manner. The connections between the tap conductors and the feeder or transformer secondary must be made using approved connectors, and they must be properly tightened to ensure a reliable connection. Finally, it is important to document the installation of the tap conductors, including the conductor size, ampacity, length, and overcurrent protection. This documentation will be helpful for future maintenance and troubleshooting. In conclusion, the code requirements for transformer secondary taps and overcurrent protection are complex and require careful attention to detail. By understanding these requirements and following best practices for installation and maintenance, it is possible to ensure the safe and reliable operation of electrical systems. The National Electrical Code is a comprehensive set of standards that is constantly updated to reflect the latest technological advancements and safety concerns. It is essential for electrical professionals to stay up to date on the latest code requirements and to apply them correctly in their work. Remember, while Note 2 of Table 450.3b restricts the number of secondary overcurrent devices to 6 for services, 240.21c3 offers an exception for industrial setups, permitting multiple overcurrent protection devices on tap conductors under specific conditions. Always consult the latest edition of the National Electrical Code and consult with qualified electrical professionals to ensure compliance with all applicable requirements. Furthermore, consider the specific requirements of the local jurisdiction, as local codes may have additional or more stringent requirements than the National Electrical Code. In addition to the above, when working with transformers and tap conductors, it is crucial to consider the following safety precautions. Firstly, always to energize the circuit before working on any electrical equipment. This includes turning off the circuit breaker or disconnecting the power supply to the transformer. Secondly, use appropriate personal protective equipment, such as safety glasses, gloves, and insulated tools. Thirdly, follow lockout/tagout procedures to prevent accidental energization of the circuit while you are working on it. Fourthly, inspect the equipment for any signs of damage or wear before starting work. Fifthly, never work on electrical equipment in wet or damp conditions. Sixthly, if you are not qualified to work on electrical equipment, hire a licensed electrician to do the work for you. By following these safety precautions, you can minimize the risk of electrical shock, burns, and other injuries. Remember, electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Furthermore, regular training and continuing education are essential for electrical professionals to stay up to date on the latest safety practices and code requirements. This includes training on the proper use of personal protective equipment, lockout/tagout procedures, and other safety-related topics.